We look next at points of inflection, which are a direct result of the last video on concavity. Just one new definition here, point of inflection, no rules or theorems, but lots of example questions. So the first thing we want to note is that the curve in the last example we did, y equals 3 plus sine of x, changes concavity at the point pi comma 3. In that case, we would call pi comma 3 a point of inflection of the curve. A simpler example of this might be the function y equals x cubed, which we can quickly graph that looks something like this. So we see here that the bending or the curvature or the concavity of this graph changes at the point 0, 0. We're concave down, and then we're concave up. And that's how we're going to define a point of inflection. Any point where the graph of the function both has a tangent line and where the concavity changes, it's going to be a point of inflection. So that means a point of inflection can occur where the concavity changes from positive or from concave up to concave down, or from concave down to concave up. A point on a curve where y double prime is positive on one side and negative on the other is a point of inflection. So that's another key way to remember where a point of inflection is. You change from positive to negative or negative to positive in y double prime. At such a point, y double prime is either 0, because derivatives have the intermediate value property, or undefined. And if y is a twice differentiable function, then y double prime at a point is a point of inflection, and y prime has a local maximum or minimum. All right, here's an example. We want to find all the points of inflection on the graph of this function, y equals e to the negative x squared. So we need to take a look at that second derivative of this function and see all the places where we change from positive to negative or negative to positive in the second derivative. Okay, first up, a derivative, y equals. This is going to be done by the chain rule. It's going to be itself e to the negative x squared times the derivative of that exponent, which is negative 2x. So there's derivative the first. Let's move into the second derivative, which we're going to have to do by the product rule, it seems, because we have e to the negative x squared times a negative 2x. All right, so the product rule is going to tell us the first function, leave it alone, times the derivative of the second function, that's just a negative 2, plus the second function, there's a negative 2x, times the derivative of the first function, and we've already done that. It's e to the negative x squared times negative 2x. All right, let's simplify that a little bit. I'm looking at a negative 2 e to the x squared, and then in the second term, negative 2x times negative 2x is a 4x squared times the e to the negative x squared. And I see I forgot my negative sign there. I do notice a common factor. It's a common factor of 2 and a common factor of an e to the negative x squared. So let's take those out, e to the negative x squared. That's going to leave us then in the first term with a negative 1 and in the second term with a 2x squared. So we'd like to know where the second derivative is 0 so we can see how to partition the number line and check for a change of sign in the second derivative. Well, the first factor cannot equal 0 because e to the negative x squared is never 0. The second factor can. We're going to write that as 2x squared minus 1 equals 0. That's going to lead us to x squared equals 1/2, and that's going to then give us x values of plus or minus the square root of 1 over 2, or plus or minus 1 over root 2, or plus or minus root 2 over 2. And we notice that those are all three equivalent ways to write the same number. So let's get to our number line and test the concavity. Here's that number line that goes from negative infinity to positive infinity. We're going to stick two critical numbers or two partition points along that. We're going to have it at negative 1 over root 2, and we're going to have it at positive 1 over root 2. And we are testing y double prime. And so I'm going to be looking at this y double prime simplified line. And the reason I'm looking at that, because I think it's going to make the math a little bit easier for me. Notice that e to the negative x squared is always going to be positive, so that's not too tough to find out. And as long as we have 2x squared greater than negative 1, then we're going to be positive here as well. So I'm going to begin with a number to the left of negative 1 over root 2. So how about we'll say negative 2. So we know that the first number is, or the first factor is positive. We take a negative 2 into this function, square it. That's going to be a 4 times 2 is 8. Plus a negative 1, that's easily going to be positive. So it looks like we're positive here. Let's move to the middle interval. And how about we pick 0 as a test value? So we plug 0 into the second derivative. 2 times e to the 0 is just a 2. And then negative 1 plus 2 times the 0 squared is going to be negative 1. So a positive times a negative number is negative. And then with the same type of logic, we'll see that if we plug in a positive value of 2 as a test, we get a positive second derivative. So what does that tell me? We're concave up on that first interval, concave down on that second interval, and concave up on that last interval. And that means we have points of inflection, or POIs, at the places where x is equal to negative 1 over the square root of 2 and where x is equal to positive 1 over the square root of 2. Now, if we needed full points, say this was a multiple choice question and we needed the y value as well, then we would have negative 1 over the square root of 2, comma, let me check my sheet here. Then the next one would be 1 over the square root of e. And that's going to be the y value for both of these points, negative 1 over root 2, comma, 1 over root e. So that's if you needed the full y value point. And you'd get that y value by plugging the x into the original function. Let's move forward, and we're going to try to read some information about the graph of a function from the graph of its derivative. So the graph of the derivative of a function f on the interval negative 4 to 4 closed is shown to the right. So this isn't just y, it's really, this is a graph of y equals f prime. So answer the following questions about the function f and justify it with information that we obtain from this graph. So not a lot of analytical work to do here. We're mostly just going to do some graph reading. So question A, on what intervals is f increasing? We know that f is increasing where f prime is positive, right? So notice this is the graph of f prime, and I see that we're positive everywhere this graph is above the x-axis. So we are positive all along here. We're positive from, let's see, negative 4 to negative 2, where the function derivative hits 0, and then from negative 2 to 1. So it would be appropriate for us to say this function is increasing on the entire closed interval from negative 4 to 1. So I'm going to write that as my answer, negative 4 to 1. What happens at negative 2? We get what we call in f kind of like a shelf point, where the function increases, kind of pauses for a moment, and then increases again. We can say it's increasing on that entire number line. Part B, on what intervals is the graph concave up? We know that the function is concave up where y prime, where the derivative, we'll actually call it f prime here, where f prime is increasing. F prime increases. So where does f prime increase? It looks to me like f prime increases from -2 to 0. F prime's moving up. And then f prime increases again from 3 to 4. So -2 to 0 and 3 to 4, that's where f is concave up. Let's give that as our answer, from -2 to 0 and from 3 to 4. All right, let's move on. At which x coordinate does f have local extrema? So by the first derivative test, we know we're looking for places where the derivative changes from positive to negative, and this is a graph of the derivative. So I'm noticing then at x value 1, the function's derivative changes from positive to negative, meaning that f, the original function, would change from increasing to decreasing at that point. So we have a local maximum there. I'm going to give that as part of my answer. A local max at x equals 1. Now, notice at -2, the derivative does hit 0, but because on either side the derivative is positive, then that's that test case of the first derivative test where we don't make a conclusion. That would be, like we already said, a shelf point. Next, on the endpoints. On the far left endpoint, we are looking at a derivative to the right that is positive. So we're increasing, the function is increasing. That makes this point a local minimum. And then on the right endpoint, we see that the function is decreasing heading into it. So that makes this a local minimum as well. So we also have local mins at x equals -4 and x equals 4. What are the x coordinates of all the inflection points of f? So that would be a place where the second derivative changes from positive to negative, or where f prime changes from positive to negative in its derivative. So it looks to me like the places where that happens is going to be -2. Where else? It's going to be at 0, because f prime changes from decreasing to increasing at -2, increasing to decreasing at 0, and then again where x is 3, because we change, f prime changes from decreasing to increasing. So that's going to be at x equals -2, x equals 0, and x equals 3. The possible graph of f on the interval -4 to 4, we're going to say for a Google Meet or live in class, and we're going to move on then to a bit of a caution. Now, it is tempting to oversimplify a point of inflection as just anywhere that the second derivative is 0, but that's not necessarily always going to be true. We still need to check for a sign change of y double prime or f double prime on either side because of one of these two possible things. The second derivative can be 0 at a non-inflection point. Take, for instance, the function y equals x to the 4th. F double prime is 12x squared, so that gives us f double prime of 0 is 0. So we have a 0 in the second derivative, but that point 0, 0 is not an inflection point. Notice that y double prime does not change signs at x equals 0. And if you can imagine y equals x to the 4th, it's a function that looks a lot like this. And we see we're concave up everywhere. So there's no need for us to say there's a point of inflection. There's not one. The second piece here is that the second derivative doesn't need to be 0 at an inflection point. For example, consider the function y equals x to the 1/3. The concavity changes at x equals 0, but there's a vertical tangent line there. So both f prime is 0 and f double prime of 0 do not exist. And we can think about that function. Pretty easy to draw. And there we have a place where we've got a change in concavity, but there is not a double prime 0 point there. That fails to exist. So the only safe way to test algebraically for a point of inflection is to confirm a sign change. That's the part we want to underline or highlight there. Make sure we know there's a sign change in the second derivative. Could occur at a point where the second derivative is 0, but it could also occur at a point where the second derivative fails to exist. Finally, here's an example on motion along a line. We know that a lot of times we see questions about particle motion where the original function is position, the derivative is velocity, and the second derivative is acceleration. And that's what we're asked to find here, velocity and acceleration, and describe the motion of the particle. So let's take a look first at the velocity function v of t. By the power rule, the derivative of x of t will be 6t squared minus 28t plus 22. We're going to look for some critical numbers there. So we'll set that equal to 0. And I'm going to wave my hand around a bit here and factor this rather than going through all of the motions. And it's going to factor into 2 times the quantity, t minus 1, times the quantity, 3t minus 11. And so that means we're going to have critical values at t equals 1 and at t equals 11/3. So we can see a little bit about the motion of this particle by looking at a number line and testing values in v prime, so the velocity function. And let's see, we got a far left endpoint of 0. We're going to partition at 1 and partition at 11/3, and this continues on. So if we pick a test value between 0 and 1, say a half, we're going to plug that number in. We're going to get 2 times a negative times a negative. That's going to give us a positive derivative. We pick a number between 1 and 11/3, say 2. That's going to give us a positive times a negative, so negative. Pick a number bigger than 11/3, say 4 or 5. That's going to give us 3 positive factors, which multiply to be positive. So this tells us about the motion of the particle. If the velocity is positive, then that particle is moving to the right because because x is increasing. Then we're decreasing, then we're increasing. But that motion along the line, when we see a negative velocity, that means we're moving to the left and then moving to the right after that. We can also take a look at the acceleration and learn some ideas about the motion of this particle there. So the acceleration function is going to be 12t minus 28. We'll set that equal to 0. We see here that we can factor out a 4. That leaves us with 3t minus 7. And that means we have a second derivative critical at t equals 7/3. So our number line again starts at 0. It moves to infinity. We have a partition at 7/3. This time we're testing a of t. And if we plug a number in between 0 and 7/3, say 1, we get 4 times 3t minus 7, 3 minus 7, that'd be 4 times negative 4, so negative. And then that tells us about the graph, we're concave down. And then a number bigger than 7/3, say 3, that's going to give us a 4 times 2, so positive, and that's going to tell us that we're concave up. So when the acceleration is negative, that means we are decelerating. And when the acceleration is positive, that means we're accelerating. And that tells us about the motion of that particle. Exercise 25 from your textbook, we will leave to class, and that takes care of this video.